Alright, hello world. I try to keep this one a little shorter today. There are two things that I did recently that I like. At the time I was confused by, but I figured them out. Either looked them up or figured them out. Probably faster if I just look into his answers to remind myself. So like one of them was the end of 23. I'll pull it up in a sec. And then I guess the other one is a comment that he makes on 27. So probably still not particularly good at those. We'll take another look at 27. Kind of waved my hands on it last time. So oh yeah, 23 is equal to the number of divisors of n plus 2. So okay. This whole block has been a little bit tricky, 22 through 25. 21 wasn't too bad, but it's like a similar. Yeah, 21 was much easier, frankly. Um, so these are the questions that we're looking at on this page. The first one was really not bad, if you're familiar with the previous couple pages. The first one, show that it's possible to write an integer in this many ways as a sum of smaller positive integers. And if the order is different, that's considered different. So there's like 7 different ways to sum up to 4, not using the term 4. And they list them, and it's kind of similar to the earlier question he had. Well, it's a little more general, though. Like there was an earlier question where he used, I guess, only these terms as well as a 4, and he was finding the number of ways to get a sum of n, sum equal to n. And you do still include all different, each permutation is a different sum. So it has a similar feel, but the way I would do this one, the way I approached this one was to do it the same way, except instead of having only 4 terms, you've got n minus 1 terms. And then there was some fiddling with, it wasn't too bad though. Like, basically just get, you want the nth coefficient of this. And you end up showing, you do a little rearranging. You end up showing that it's equal to this, and you can do that. But he has another much shorter answer to that for 21, where you just look at like the points on an interval, and you say, well, you either include this point in the division or you don't. So if you included like every point, that would be more like this first sum. And if you only included like say 2 points on your interval, that would look more like these last couple cases. Anyway, we talked about that last time. That one's not too bad. 22 is a similar thing. You do like, I talked about that last time too, so I won't go back over it in detail, but you do something like this. And the denominators all make sense in this case, because when you look at the equations, you just get either x plus 2y, or 2x plus 3y, or 3x plus 4y. So use those coefficients to dictate what the exponents are in your zeta in the bottom there. The top comes from a shift, because instead of looking at the nth coefficient, you keep looking, in the first case you're looking for the nth, but then you're looking for the n minus first, and the n minus second, etc., all the way down to 1. So he's scaling it so that you are actually finding the nth coefficient of this series. We originally wanted the n minus first coefficient where there's a 1 on top, so he shifts it by multiplying like that. And that's about it for review. Then we're on to 23. I guess I won't go all the way back over it, but there was a comment at the end that I didn't follow at the time, and it's actually not that bad. Um, Maybe I should see if I can redo this one. I was looking at 23. They wanted the total number of coefficients, or total number of non-negative integral solutions to this set of equations. You've got x plus 2y, or 2x plus 3y, or etc. But the right-hand side is basically odd. It's like n minus 1, n minus 3, n minus 5. So you can do the same trick as you did in the previous example. Like you're going to do some sort of scaling. Like you may as well find the nth coefficient of, this big sum of a bunch of different series. Like one series from this set, one series from this set, one series from this set, etc. But since we don't want just the nth coefficient, it's changing, we're going to scale each one of them. So the first one he ends up just ignoring. So say you want to solve, you want to find the number of integral solutions to this, like non-negative integral solutions to actually, I guess it was n minus 1, I think. The first thing you do is jot down this. Like if x was the only term, this geometric series would give you, the coefficients of this would give you the number of solutions for the right-hand side. So say the nth coefficient would give you the number of solutions. Of course, it's only 1, so it's not super interesting. It's just 1 all the way through. Since there's another term here, we're going to get another one like this squared. And so you'd have to expand this, and then you could look for the nth coefficient. In our case, though, we're looking for the n minus first coefficient. I think what he ends up doing, because he wants it to be like even, you'll see what I mean in a sec. So like the next example was this. And so my instinct was to immediately put a zeta here, put a zeta cubed on the next one, and continue like 3x plus 4y equals n minus 5, right? So my idea was to put a zeta here, zeta cubed, zeta to the 5th in the numerators on each of these examples. But for some reason he doesn't do that. He actually just finds the n minus first coefficient, which is fine. It's equivalent to me finding the nth coefficient. But I don't know, I should see maybe why he did it his way. So yeah, we continue with more of these, but my point is going to be, I was going to put a zeta here, zeta cubed. He doesn't do that. He just looks for the n minus first coefficient in this general expansion, and he scales it by even powers. So he scales this by 2, so that if you find the n minus first coefficient for this, it'll be the same as the n minus third coefficient for the series that you were considering. Anyway, yada yada. So you're getting a sum like this, zeta to some even power, and then downstairs you get 1 minus zeta to the v, I want to say plus 1, right? If v is 1, you get this. So we're going to go boop, and then 1 minus zeta to the v plus 2. And this goes from 0, well, I'm going to put an infinity here, but I suppose it could be finite. You could stop after like a certain number of terms if you really wanted. So anyway, I'm back to looking at 23. The number of solutions is equal to the coefficient, well, the n minus first coefficient in the expansion, and here it is, and this is the one I just wrote out. So the first thing he does is make it telescoping. I don't know why I'm reviewing this. I just did this one last time because I figured out where it came from. That I was stuck for a while going from here to here, but I guess we'll see if I can do it again. Um, should have just gotten to the point, but it's this, and then to make it sort of telescoping, right? If you did have this telescoping thing, we want to make this look like this. If you did, though, add these fractions, you would get, let's see, this times that denominator minus this times that denominator. So you'd get this chunk minus that chunk, which means upstairs you would have this after the ones cancel out. That would be what the top looks like. Okay, so we want to make, he's trying to make this look like that in the numerator, and that's where this extra factor comes from out front. I mean, I guess in some sense you could say he just multiplied and divided by this numerator to force it to become a telescoping thing. Okay, so I guess just notice this. So we have this series, and the only thing we're doing now is like, you want to express it as a power series so that you can just look at a particular, I should have put like a K or a V here, but you want to express this as an actual power series and get a grip on what the coefficients are. If you get a formula for what that n minus first coefficient is, you have your answer to this question of how many solutions would there be in this with this given set of equations. So yeah, I'm saying, I guess never mind this part, let's ignore that numerator for now. If I can introduce this, then I know I can split it into this telescoping thing. So let's do that. Multiply and divide by that. I guess if you factor zeta to the v out, you'll get a single zeta minus zeta squared. So maybe we should actually just factor this out like that, okay? And then we'll have zeta, we'll have 1 minus zeta, yep. So I'm going to multiply and divide by this. We're not going to actually change anything. We're just going to change the way it looks in a second. This is what we started with, and I multiplied by 1 in a clever way. Just the standard trick in math, multiply by 1. Yeah, somehow this junk, well, the reason we did that, I shouldn't have left it like this. This stuff on top, we're going to pull inside, and we're going to be able to say, okay, now it's telescoping. Stuff out front, let me leave this one out front, but the other one we'll bring inside. So you got zeta to the 2v, I guess minus v minus 1. We'll make some sense of that in a second, but it probably agrees with what he wrote there. Yeah, it does, right? V minus 1 is exactly what you get there. And then the other stuff was this stuff, which the whole reason I did this is that it gives you a telescoping thing. So I'm going to go ahead and make it telescoping now. And this part is what we had. So now we're here in the solution. Okay, we are zeta to the v minus 1 times a telescoping thing. And then I had gotten, like last week, I had gotten sort of very confused about how he gets to the next part. And I went over it again a couple days later, but I'll just show you again. So I was like, how does he get this, like from here to there? Like I tried taking a term off. I spent like an hour stabbing at this thing. And I finally figured it out like the next day. And I posted a video about it. I mean, I streamed it. But then I ignored this last part. And it's actually really not bad. So that's the whole point. I'm going 20 minutes of review here just to just to explain this one part. But anyway, we're here at this stage. Just as a quick review, what on earth am I even doing? Number 23 here is what I was trying to solve. Find the total number of solutions to this set of equations. Like x plus 2y is n minus 1, or 2x plus 3y is n minus 3, or 3x plus 4y is n minus 5, etc. It's evidently fewer than n plus 2 solutions. And the difference is equal to the number of divisors of n plus 2. I guess so that's the part I want to explore today, I guess, is the last sentence and like the last chunk of this answer. So let's see if I can still remember how to get to the next, from here to there. Basically what happens is you've got this infinite series, right? It would be cool if you could just split it up. And it turns out you can, because you're looking at, in general you can't. You can't just do this. That should be raising lots of red flags. It's not true in general, of course. But what's happening here is you've basically got a geometric series. Like this chunk is bounded. It's true if each of these is absolutely convergent. If these themselves are convergent. The counterexamples you'll find where you can't do that, it's because generally like one of them, it could be because the right-hand side doesn't make sense, You can come up with obvious examples where this converges but that doesn't. But I'm saying it will be true, it will be equal, that you can split it into two pieces like that, like you kind of intuitively want to, if these are each convergent. And what's happening here is we have zeta on top and we have 1 minus zeta on the bottom. If I distribute this, you're looking at a situation like z to the k over 1 minus z to the k, right? And then you got another one that you're subtracting, like this minus something very similar. So this is the kind of series that I want to see, does it converge or not? And it kind of clearly does, because this, well, it converges if z is less than 1. Obviously you can't plug 1 in. But if you stay away from 1 for a fixed value, this is bounded. So you're just looking at, something that's comparable to a geometric series. You're basically just looking at, let's say it's bounded by m. The series is less than m times a geometric series. So of course it's convergent. So that's why you're safe to split this up into two chunks. You can do this piece minus this other piece. You can just sort of distribute this in and you get two different series. And that's part of what he's doing to make that happen. And then after that, he basically just pulls off one term and does a little bit of factoring. So let's see if I can get there again. The point is going to be, though, to look at this series. This chunk of the answer is what if you wanted like the 10th coefficient, well, this is where you need to find it. It's not coming from the first term. And so he talks about that. So I'll see if I can remember about that part when I get there. But in the meantime, let's look at our series again. It was 1 over 1 minus zeta, the sum of, and now we have two pieces. We've got zeta to the v minus 1 over this 1 minus zeta to the v plus 1. And separate from that, okay, we have zeta to the v minus 1 over 1 minus zeta to the v plus 2, like that. Both of these start at 0. I don't know why I'm doing this again, but the point is actually just to sort of make, well, you want these to have the same power so that you can factor out the little telescoping part, the little 1 over 1 minus zeta part. So make them match up. So you're going to do a reindexing on this part to make these powers the same, right? Then you have a common factor between the two series. And then the other thing is you're going to get the numerator to match up with this part. We'll do that last. Again, this is just to get this answer, get from here to there. So maybe I'll leave this numerator alone for the moment, but the first thing I want to do is re-index this so that that power becomes v plus 2. At 0, of course, you get 1, but if I plug in v equals 1, that's the second term, right? You get zeta squared, which is the first term you get over here. So what he's going to do is remove the first term from this series. Like, the first term, if I plug in 0, it looks like I get zeta to the negative 1 over 1 minus zeta to the 1. Then we still have the whole rest of the series, right? We'll go ahead and keep it the same for the moment. But we're going to re-index this. We're just going to change it, we're going to change this to 0 again so that the indices match up. Like now, if I plug in 1 to this, I get 2 as a power, right? So instead of writing it like this, we're going to write it as like, say, k equals 0, and we'll just add 1 to the power, right? So here if I plug in 1, I get 0, so clearly the numerator is supposed to be zeta to the k, and downstairs we're supposed to get a 2. If I plug in 0, of course I don't get 2, so it must be v plus 2. So there's your re-indexing. It's the same series. I just shifted by 1, right? And then over here we had minus, starting at 0, v minus 1 over 1 minus zeta to the v plus 2, yada yada, right? Anyway, now these are the same, right? And they have the same starting index even. So, oh, sorry, I wrote a v here. Sorry. It's supposed to be a k in my new index notation. But anyway, we're going to turn back into v, and we're going to group these guys together. The numerator is different, of course. The numerator is just v instead of v minus 1. But, so it's equal to, yada, we now have this extra term, like that. That's one term sitting there. And then I guess what we're adding is a series that starts at 0 again, still. The numerator, though, is now to the v minus zeta to the v minus 1, like that. And then downstairs, you just have a single 1 minus zeta to the v plus 2. So I just recombined those two series. It was initially this telescoping looking thing with the numerator being just one term. Now it's no longer telescoping, but the numerator is 2 terms. It's a difference of 2 terms, So we could probably introduce a factor like this. Like we could factor this out. I don't remember that being in the answer though. Yeah, it's not. I do know that he's about to factor out zeta to the v, zeta cubed, so that this matches up. But now I feel a little strange about this extra guy. Like, shouldn't this have... I don't quite remember where that factor goes. It didn't seem to go anywhere here. Anyway, I'll just keep going with what... oh, there it is. Duh. I'm sorry. This gets distributed, of course, into both terms, right? I was like, why is this still here? Shouldn't I be able to divide by 1 minus zeta? Oh yeah, there it is, 1 minus zeta. Anyway, distribute this into both terms, okay? First actual term and the second series. When you distribute this, the first term is just like this. There's 2 of those now, right? And then over here I've got 1 as well, right? But I'm saying this numerator, we can factor that out, right? So it's, and I guess you can only really factor this part out, right? So we've got zeta to the v minus 1 times zeta minus 1. So those are going to cancel. and then you'll get a minus sign. Like, this is the negative of that. So they cancel, but you're going to have to factor a negative sign out. So I'm here, minus, those are gone, and this is still there, zeta to the v minus 1. So now is where we finally want to make this match up with that. You can just factor zeta cubed out, and that'll become zeta to the v plus 2. So I basically just multiplied and divided by zeta cubed. And the only reason, the purpose was to change this power to match that power. So now you're looking at this series, which looks a lot nicer. You know, it's like what I talked about on the other side. It's z to the k over 1 minus z to the k. It basically looks just like this series that we started with. Well, not really. See the difference in the powers there? But now the powers match up. Of course, you got this ugly factor out front, but what can you do? So this starts at 0, starts at 0, starts at 0. And now he did one last trick to make it look like this. You can see how we're basically almost done, right? Well, there's two little things wrong with my answer. Two little things wrong is that we only have one power of zeta there. And the other thing is we don't start at 1, and we don't have quite this power. So I either need to do some sort of reindexing. Basically all you do is you reindex and you get rid of like one term on this series. You pull one term out. And when it combines with this guy, you'll see that it works out to be what's in the book. I did talk about this last time, but I don't know. I guess it doesn't hurt to go over it again. So what are you saying? Well, he starts this at 1, and then he pulls a term out. Oops, sorry. He starts this series at 1 instead of 0, and he also, this doesn't look quite right yet because we didn't pull a term out yet. So to do that, first of all, reindex this. If you change this to start at 1 instead of at 0, let's see, when I plug in 0, I expected zeta squared, 1 minus zeta squared, right? When I plug in 0, I expect a 2. So here, when I plug in 1, I guess we're going to get this, right? V plus 1 would be the same series. So I haven't done anything else. I haven't shifted any it might almost be smarter for me to just a second. I was going to say, it might almost be smarter for me to just start at v equals 2 instead. Should we do that instead? But what I'm going to do is add a term, like add and subtract the same term so that you're adding 0, but it changes this index to start at 1. So I'm actually going to just jump right to this one. So instead of v plus 1, we'll have v over 1 minus zeta to the v. And now it actually matches up with what he has in the book. The problem is his index starts at 1, and mine starts at 2, and that's the only difference. So what we're going to do is, here's this term out front, right? And then here's our term, our next one. I won't do any trickery yet. I'll just write exactly what we just talked about. Yeah, so what he's going to do is add and subtract this this sequence, this term, but when v equals 1. If you plug 1 in there, you'd get zeta over 1 minus zeta, right? So I'm going to add and subtract that. So we just added 0. But this one I'm going to absorb into the series so that we change the index to start at 1 because we're subtracting that, right? So this stuff I'm going to group together. I shouldn't do that. But you get the idea. This stuff is going to become part of the series. Or if you want, I can put a plus here and do that. But anyway, we're subtracting and adding this. And so this part is going to get added to this part. So these guys get lumped together. And these guys get lumped together. And since you're subtracting, you really gets absorbed in there. Am I missing something? There's this extra guy I forgot about, huh? Yeah, it needs to be there if you're gonna just subtract this in. So I guess I'm gonna need to put a zeta cubed here and here. Okay. Otherwise, it doesn't really. This zeta cubed is being multiplied by every single term. So if I want to tack on an extra term, it better have a zeta cubed in the denominator. I almost forgot that. Sorry, I didn't see it there until just now. But yeah, so I'm subtracting and adding that. That's what I meant to be adding and subtracting. Now when you subtract it, it just gets sort of absorbed into this series. And so it just changes the index at the bottom to be a 1 instead of a 2. Other than that, we get this. And then my claim is if you add these two, you'll get the thing that he has out front here. And that's just adding fractions. So, you know, this guy has 2 factors of zeta and 1 factor of this difference. This guy has 2 factors of the difference and only 1 factor of zeta. So it's just some simple addition. But I'll go ahead and move to a new sheet here. If you add those, well, here, I'll let you see it. This makes more sense. Adding these two, okay? So this guy's missing a factor of zeta. If you put a zeta on top, you will now have zeta squared downstairs. And this one, it was 1 over zeta squared, but it's missing an extra factor of 1 minus zeta upstairs. So now that it has that, they have the same denominator. We just add those fractions, and we'll get, looks like we'll get 1 plus zeta minus zeta. So you're getting 1 zeta squared downstairs and 1 minus zeta squared also downstairs. And that junk is that term right there. And you can see the rest of it is the 1 over zeta cubed times the series starting at 1, zeta to the v, 1 minus zeta to the v. So I finally got from here to there. Should probably put this on autofocus. So we now have this as our sort of generating function. This is, I guess it's a minus. Yeah, it's a minus. See that? This is our generating function for the solutions. Like the coefficients of this big mess would give you the answer to this question that we had way at the beginning. Like, how many solutions are there to this set of equations? Well, you have to produce this series, and then you can at least argue that the coefficients of this series would be the answer. Okay? So we're there. And you're like, so what? Now how am I supposed to get the answer? Which is always the follow-up question, sadly. What am I supposed to do with this crazy thing? How do I get the answer? That's what his next line has to do with. And at the time I read it and I was like, I don't know what that means. Like, I don't know why that's true. He said this series is something, you know, it's some power series. The tau v represents the number of divisors of v. And I was like, okay, why? What are you talking about? And he refers to like something much later in this book. Well, it's in the second volume of the book. So I was like, okay, that must be some crazy number theory thing that I'm not going to understand. But no. It's actually like a 5-minute conversation. So the reason he's bringing this up is, of course, this is the same series we're looking at. If you want the n minus first coefficient, which is what we were after, then I guess you want, let's call it, let's say this series is Well, we should be a little careful about what I write here because he shifted it by 3 by doing this effectively. So that might be why his answer. We wanted the n minus first coefficient of this series. And this one's sort of been shifted by 3. So it's almost like you want the n plus 2 coefficient of this series. If you're going to look at just this part alone, we want the n plus 2 coefficient, I believe, of just this guy. Okay? So now that's why he's focusing on just this part, of course, because like that's where all the coefficients are coming from. But that's also why he's talking about n plus 2 at this point. He's no longer talking about n minus 1 for some reason. The reason is you were shifted by 3. Anyway, so what about this series? What is this series? How do you even get these coefficients? He calls them tau. But why is tau, why is tau n, or why is tau v equal to the number of divisors of v? Really? And that kind of, I assume it must be some genius thing, because where is that even coming from? I'm not familiar with this, but maybe I should be. Maybe if I took some number theory, I would be more familiar with it. This cat right here. Well, anyway, if you ignore the series, if you ignore the sum sign, that's a geometric series. This right here is a geometric series, of course. If we ignore the numerator, well, we won't ignore it, but if it was just a 1 on top, you would get 1 plus zeta to the v plus zeta to the 2v, zeta to the 3v, etc. So it's just a geometric series that's been shifted. So it's actually zeta to the v plus zeta to the 2v, zeta to the 3v, etc. Okay, that's a common trick to just shift a geometric series like that. So this is what we're looking at, and now we're summing that as v goes from 1 to infinity. And I saw that, but I was like, that's really confusing. I can't tell what's going on here. Like, a bunch of terms are grouping. It's just complicated, right? Let's see if it's complicated. You have v going from 1 to infinity, and then the series that you're talking about is let's call it, I want to just call it like k, but it's multiples of v, right? It's like vk, where k goes from 1, 2, 3 onward. I wonder if I made that clear at all. Is that clear? Like, fix a v. Just call it v, I mean. For a fixed v, you get k is 1, k is 2, k is 3, etc., right? Yeah. So it's this. So it's the same as this, is what I'm saying. You now have your power series, by the way. Although it's not, unfortunately, it's not one series, it's like a double sum. So yeah, what I wanted to just say is like, well, you're doing this where n is vk. Oops, sorry. There's a coefficient out front. Let's call it tau n, right? Tau n zeta to the n. That's exactly what we have. But the only times, like it seemed really simple to me, the only times that you have a term is when this happens, which means that um, hmm, I mean, that's why it's counting the number of divisors. That was not a great explanation. I'm saying the only way that this product could equal n is if um, like for each pair k and v, I kind of changed my notation here. Maybe it would have been clearer if I wrote n equals 1 and then this part was v. But the point is, you're counting the number of ways that you can divide n. These are whole numbers. So like for each pair v and k where this happens, we get a power of zeta that equals n in this series. How many times does that happen? Well, all the ways that you can do this, which is all the ways that n has divisors. Does that make sense? It's like over here we're considering every pair of v and k, and the power itself is just v times k. So for each pair where the power becomes n, you have a pair of divisors for n. And that's it. That's the whole explanation. For each pair of vk where this happens, which is that this becomes zeta to the n, or vk equals n, n has a divisor, and that's it. So every time this occurs in your series, it happens like it has a 1 out here in front of this. This coefficient is 1, but each time that happens, each one time that happens, you're contributing one more time to this zeta to the n. So however many times you can do that is what this coefficient is, and hey, that's the number of divisors of n. Yeah, not quite so crazy. I don't know. For some reason, I wasn't familiar with this. But then again, I didn't take number theory. I have a feeling this probably popped up. Like it's probably some fundamental thing that I just wasn't familiar with. So that was one thing I wanted to talk about today, was this part, which I thought was really cool. Like this series, if you expand this series, it tells you the numbers of divisors of each power. That's kind of cool. Like this series is what we're calling tau n times zeta to the n, and the tau tells you the number of divisors of n. I don't know, I just thought that was kind of awesome. But it's pretty simple actually, because it's this double sum, and then for each pair of numbers where the power is n, well, you have a divisor of n. So yeah, end of story. The other thing I wanted to show you was in his answer for 27, which I guess I said I was going to look at today, but I guess we can try. But he makes a comment in his answer on 27 that at the time I was like, I don't know where that's coming from. I should be familiar with it. But it's actually pretty straightforward. At the end of this, he says, notice this volume characterized by these inequalities. Well, that would probably make more sense if we saw the question. So for 27, he's doing a similar thing where we're solving equations, but this time it's only one equation. He says, take a bunch of numbers, a1 through al, without a common factor, so they're relatively prime, without a common factor other than 1. And then let capital AN be the number of solutions to this equation. So a1 x1 plus a2 x2 plus yada 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 plus ALXL, okay, equals n. So again, he's making a series. He wants us to like come up, well, one could come up with a generating function using this a sub n as a coefficient for the series, for the power series. And then he mentions that this is true, which is still kind of blowing my mind, but it's not a hard one. That's not even the hard part, really. I know why I didn't want to do this. We really need to like redo 25 first, like get comfortable with it. Then 27 makes a lot more sense, because this factoring thing is like really not that deep at all. It's just partial fraction decomposition. But if you haven't done that in a while, then so maybe I'll review that off stream, and then I'll come back and explain this one, this harder one. But blah blah blah. The point is, this was his question for 27, is to show that this limit would happen. And like if you take the number of solutions and you divide by n raised to the power L minus 1. So L was the number of variables, the number of AIs, you know. Anyway, if you take that limit, you'll get this, which makes it's actually not that complicated if you do the partial fraction decomposition thing. He kind of explains it. He doesn't really do very much, actually. He says, here's your series that we're talking about. It's going to be equal to this. That's the thing we've been using for a couple days now. So it's the same trick. If you had like x plus 2y equals n, then you'd get this for the x plus 2y bit. Or if you have 2x plus 3y, then you get this bit, that denominator. Or if you have 3x plus 4y, then you get that denominator. You get 1 minus zeta to the 3, 1 minus zeta to the 4, corresponds to the 3x and the 4y, okay? So of course this junk on the right just corresponds to a1 x1 plus a2 x2 plus yada 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 plus al xl, okay? So at first blush, that's all you do is just say like, well, this product has some power series and the coefficients would give you the answer. That's true. That's true. But their solution is actually, if you do a partial fraction decomposition on this right-hand side, you'll see that the principal term, like this term, the term with the largest power in the denominator, will have this as a coefficient. And that pretty much is the end of that is the answer. Like that's the end of the computation. So it's actually not a bad one. You just have to be comfortable with partial fraction decomposition. Let's see. Yeah, so I kind of want to look at that again, just so I can do it sort of in general and make sure that I'm not. But it's really pretty obvious. You could even do it with. You should do it with a smaller example. Like I started to do it with 2 or 3 fractions and saw that like, oh yeah, of course, it's almost like not like a factorial thing, but you know how it is when you like take when you do like the power rule a handful of times, like maybe you're doing a Taylor series thing in calculus and the powers keep popping out. It's basically what's going to happen here. But yeah, what I wanted to talk about was this part. He makes a comment, notice the L-dimensional volume characterized by these inequalities. So don't take an equality, but instead take an inequality, like the question we were just talking about. Instead of saying equal to n, look at the volume when this is less than or equal to n. And in the first, I don't know what to call that, octant, where everything's positive. It's not an octant because it's in L dimensions, but in the first region. And he says, notice that the volume characterized by these would be this. And I was like, how on earth would you even get that? And then he says an is comparable to the derivative of this volume. And that one I'm going to have to think about again. It's going to be something obvious. But anyway, the first part I totally understand now. It's really not that bad. So let me give you a smaller example of that. like let's just talk about, first of all, here's a super easy one. If you had x plus y equals like n, right? Well, that's just this, where this is n. Did I screw that up? Like subtract, you get n minus x, so it's like this, right? So if we were in only two dimensions, okay, we had x1 plus x2, and you wanted to consider the volume of, well, I guess it'd be an area in this case, right? The volume of given by these constraints, it would look like this region. It'd be this region, right? This is really easy to get this volume, this area. You're just going to integrate. If you let x1 vary from 0 to n, then your height is capped by an equation like y is less than n minus x1, right? So you get a form like this. The last variable is less than or equal to your number minus whatever other variables are there. So if we were in a larger number of dimensions, let's just stop at 3 for the moment. It's of course the same. You get something like this. And it's harder for me to draw this, but it's kind of the same idea. It's like it's this triangular shape. Say again, I'm like, I don't know if this is an algebraic geometry thing. I'm not really familiar with the term. I think it's a simplex or something. If it was one, I think it's called a simplex. But you know, I'm picturing something like this. It goes down in each direction. It's like a, right? You're getting a little wedge shape. Well, now you've got a double integral. So this integral was 0 to n on the outside. And I guess we only had the one variable. Oh, I'm sorry, not n. Well, yeah, that's n. But the inside was, here, let's do it this way. The inside is like 0, the y values go from, 0 to this height, which is n minus x. Or, you know, the x2 values go from, so I'm saying it goes from 0 to n minus x1, like that. Or let's just call it x in that case. So we're getting a double integral. The outermost goes from 0 to n, but the insides all go like n minus, let's say x1, and that'll be your dx2, dx1. That's the same, that's the area that we'd be talking about. So this is a very similar thing. It's just going to be 0 to n, 0 to, I mean, this time I get a triple, I suppose, but here we just get one variable, but here we get both. And that's dx3, dx2, dx1. Put a little 1 there if you want. Okay, so if I was integrating this, you're integrating 1, so you just get x, you just evaluate from 0 to here, you end up with just this number, which I'm then integrating again in the variable x1. And I wonder if does it alternate or not? Let's see, we have this. There is a negative there. So when you take the antiderivative, you're getting, I want to say you get a negative, right? Because if I don't have that there, yeah, you do get a negative. But anyway, evaluate from 0 to n. Yeah, of course, that negative cancels out, because at n you get 0, right? At the upper bound, weirdly, you get 0. So you're getting the negative of 0 minus n squared. So I'm getting n squared. Something's fishy about this. No, this is correct. This is fine. This is true. Why is that? Isn't that wrong? Shouldn't I have a half in here? Oh, you forgot the half. Good. Good. I was going to say, shouldn't it be half? Yeah, I forgot the 2. Duh. There's a 2 over there. So we do get n squared, but it's n squared over 2. Is this volume. All right, so if n was 1, you'd get a triangle. You'd expect the area to be half. That's kind of a silly example, but yeah, right. Same thing's happening with this. It just happens a bunch of times. So if you had 3, it's going to be n cubed. And downstairs, it's not going to be 2. You're going to be using that power rule, well, 2 times this time, not just once. So you're going to get like a 3 factorial downstairs. See what I'm saying? We can try to do it one more time, but I just thought this would be enough to explain. That's how he's getting this answer. Well, there's one more thing I should explain, because he's got a bunch of a's there. But if you imagine all the ai's were 1, you can see now where this answer is coming from. Whoa. If you imagine that all the a's were just 1, like if the equation was x1 plus x2 plus x3, like the example I was doing. So that's a simpler case. But you would get exactly this, of course. You would get n to the power L, and you would get divided by L factorial, which is what I'm claiming I'm getting here. So I'll do it one more time, the easy part. So yeah, of course, the first one, you integrate, you just get this. And that was in the x3, you can't see any of this, sorry. That was just in the x3 variable, so x3 is gone now. But I still want to integrate this in x2 and x1. And so yeah, you're using a power rule on this whole mess. There's our variable. There's a negative in front of it. So sure, put a negative in front of it. But the point is you just get this stuff squared over 2. It stays the same. It's like a nice linear thing. It's pretty easy to integrate. But yeah, we do get a 2 because this power just increased by 1. And I didn't evaluate it, did I? No, I didn't. I screwed it up. Did you think you were evaluating or something? What's going on here? You're supposed to evaluate this from 0 to n minus x1. Right? Yeah, that x2 can't, that can't still be there. I haven't finished apparently, right? Okay, so I took an antiderivative. I got this formula. Now I'm taking a definite integral from 0 to this upper bound. And if you plug in n minus x1 for x2, it is of course going to cancel and give you 0, just like this previous example. So you're going to get, this mess in parentheses. Well, this mess in parentheses. There's a half there. Maybe we'll pull that out front. But, if you plug in this upper bound, you get 0. If you plug in the lower bound, you get, this goes away. And all you get is the n minus x1 part. So it's like negative 0 plus n minus x1 squared. So I'm here, is what I'm saying you're getting. That would be my answer for that. Plus there's still a 2 downstairs. The 2 matches up with that power. But now I want to integrate this part. So if you do it one more time, I presume you will get stuff to the 3 over 3, right? You evaluate from 0 to n. And there should be a negative there, okay? Because there's a negative in front of the x1, in front of the variable that you're integrating in. There's going to be a negative there as well. Like, think maybe the chain rule. You could use the chain rule, I guess, if you wanted to. Well, it is the chain rule, but I'm saying you could use like a u sub if you really wanted to prove this to yourself. But it's obviously there. There's a negative there, right? If I take this derivative, you'll get back this stuff. So anyway, when you plug in n, of course, you get 0. When you plug in 0, you get n. And because of that negative sign, like swaps around, it becomes actually positive n. It's n cubed over 3 times 2. We're getting n cubed over 3 factorial. So what does this have to do with his answer? The last thing you would need to know is that he's doing a u substitution, basically. Or I suppose in this many dimensions, it has to do with like the Jacobian is this product, is this factorial, the Jacobian of, well, I won't go there, but the point is he's doing a substitution. He's saying let u1 be a1 x1 and let u2 be a2 x2 and let u3 be a3 x3, so that this equation becomes exactly what we had above. You know, it's much simpler looking. So same equation. Like now you'll get this answer, but the catch is you did a u substitution to get there, so you're going to have some extra factors popping out, right? Like 1 over a1 du is how you're going to have to replace the dx1 variable up in our computation. Or, you know, if I did this again, but with these numbers, then you, instead of n minus x1, you'd have n minus a1 x1, right? That's a pain. So to correct that, to make it simpler, make it look like this, you have to do a transformation. It is linear, it's a pretty straightforward one, but these are the factors that pop out front, and that's where those extra terms are coming from, okay? I mean, if you already know what I'm talking about, you're just saying like, yeah, Jacobian. But there's a transformation from this space into this space, and the Jacobian of that transformation would be this product. That's what's missing. When you change the integral over here into an integral that's simpler looking in this space, this is the multiplier that's going to pop out. The one-dimensional version of that is u sub, of course. But that, my friends, is where, oh no, it froze. It froze on me. That is where this junk is coming from. The division by a1, a2, yada yada, up to al. So that explains this part. And that was the last thing I wanted to talk about today. These two little blurbs, a lot of the greatest parts about this book are his, like, the last sentence of the answer where he just says something almost casually or like off the cuff, and it's like stuff I should probably be familiar with. There is like a lot to unpack there, but if you already know it, then like, you know, it's a one sentence comment. It doesn't really need any more explanation because this is just calculus. Like this is multivariable calculus, frankly, this comment, to get that. And I'm sure this one is too. I just haven't thought about it enough yet. It's probably something obvious. The number of solutions to, it's like this is, we're looking at the boundary, this equals to n. We're trying to find the number of integer points that are on that boundary. And he's saying, well, it's comparable to the derivative of the volume. You know, that should be obvious to me. It probably is obvious, but I don't know it right now. But if I figure that one out, I will mention that in the next video. Hopefully around the same time that I actually do 27. Well, 27 is probably not so bad, but I haven't done it on stream yet, so I will do 27 with a partial fraction decomposition to explain this term. And hopefully I'll have this figured out by then too. So then we can have 27 part 1 completely done. But no rest for us because we still have part 0.1 and 0.2 to do. 27.2 takes us like a whole page, so that's going to be a nightmare. But then, thank God, it's over. And I think finally it starts to feel a little more normal. Well, 30's also a little bit gory, but after this, we're starting to get into territory I feel a little more comfortable about. But ultimately, he's kind of just shuffling some series around, you know. He's doing the same trick on all these problems. You just look at this kind of series. And in this case, he had like, oh, he's got like n different equations. So okay, you have n different series like that. You add them all up, and you do some bookkeeping to get a form like this, and then you do shuffle some algebra around, and this pops out. Yeah, it's easier said than done. Like when you know the answer, it's not so bad, but getting there, like when I was doing 23, I got the first part, and I was like, okay, so what? So it's this infinite series. What am I going to do with that? I would not have gotten here. I mean, I get this, I got that part, but then being like, oh, well, it's just a telescoping trick. Like, oh, okay, now I get it. Anyway,